Section 15.3. Energy of the simple harmonic oscillator. In this session, we will explore the energy dynamics of a simple harmonic oscillator. We will begin by defining kinetic energy in simple harmonic motion and the potential energy specifically within a block and spring system. From there, we will discuss the total mechanical energy and the principle of conservation that governs these systems. We will also derive an expression for velocity as a function of position. Finally, we will look at how these macroscopic principles allow us to model microscopic phenomena, such as atomic bonds, by treating them as harmonic oscillators. To understand the kinetic energy of an oscillator, let us consider a block attached to a spring on a frictionless surface. We treat this as an isolated system where the spring itself is massless. The kinetic energy, represented by capital K, is equal to 1/2 times the mass times the square of the velocity. By substituting the expression for velocity in simple harmonic motion, we find that kinetic energy equals 1/2 times the mass times the square of the angular frequency times the square of the amplitude, all multiplied by the square of the sine of the quantity angular frequency times time plus the phase constant. Because this expression involves squared terms, the kinetic energy is always a positive value or zero. Next, we consider the potential energy of the oscillator. In a block and spring system, elastic potential energy is stored in the spring whenever it is elongated or compressed by a distance x from its equilibrium position. Using the standard position expression for simple harmonic motion, which is amplitude times the cosine of the quantity angular frequency times time plus the phase constant, we can define the potential energy. The elastic potential energy is equal to 1/2 times the spring constant times the square of the displacement. This results in the formula 1/2 times the spring constant times the square of the amplitude times the square of the cosine of the quantity angular frequency times time plus the phase constant. Similar to kinetic energy, this potential energy is always non-negative. The total mechanical energy of the system is the sum of its kinetic and potential energies. When we add the expressions for kinetic energy and potential energy together, we can factor out 1/2 times the spring constant times the square of the amplitude. This leaves us with the sum of the square of the sine function and the square of the cosine function. According to the fundamental trigonometric identity, the sum of sine squared and cosine squared of the same angle is always equal to 1. Therefore, the total energy is constant and equals 1/2 times the spring constant times the square of the amplitude. This shows that the total energy does not change over time and is directly proportional to the square of the oscillation amplitude. These energy transformations can be visualized through plots against both time and position. The first graph shows kinetic and potential energy oscillating over time. Notice that as potential energy decreases, kinetic energy increases, and vice versa. At the turning points where the displacement equals positive or negative amplitude, the velocity is zero, meaning the energy is entirely potential. Conversely, at the equilibrium position where x equals 0, the potential energy is 0, and the energy is entirely kinetic. The second graph plots these energies against position, showing a parabolic curve for potential energy and an inverted parabola for kinetic energy. In both representations, the sum of the two energies always remains a horizontal line, representing the constant total mechanical energy. We can further analyze these energy states using bar graphs at specific points in the motion cycle. At the start of a cycle, or at the half-period mark, the block is at its maximum displacement where it momentarily stops. At these instants, the kinetic energy bar is at 0, while the potential energy bar is at 100% of the total energy. When the block passes through the equilibrium point, at 1/4 or 3/4 of the period, it moves at its maximum speed. Here, the potential energy is 0, and the kinetic energy accounts for the total energy. At any arbitrary point in between, both bars will be partially filled, but their combined height will always equal the total mechanical energy bar. By applying the principle of energy conservation, we can determine the velocity of the oscillator at any specific position, x. We set the sum of the kinetic energy, 1/2 mass times velocity squared, and the potential energy, 1/2 spring constant times displacement squared, equal to the constant total energy, 1/2 spring constant times amplitude squared. Solving this equation for velocity gives us plus or minus the square root of the quantity spring constant divided by mass, multiplied by the difference between the square of the amplitude and the square of the position. This can also be written as plus or minus the angular frequency times the square root of the quantity amplitude squared minus position squared. This relationship confirms that speed is greatest at the center and zero at the edges. The concept of simple harmonic motion is not just for springs. It is a powerful tool for modeling atomic bonds. While the actual forces between atoms can be complex, such as those described by the Lennard-Jones potential, they can be simplified for small displacements. If an atom stays near its equilibrium position, its potential energy curve looks very much like a parabola. This approximation allows scientists to model solids as a lattice of atoms connected by tiny, invisible springs. This slide shows a graph where the complex potential curve is compared to a dashed parabolic curve, demonstrating how well the harmonic oscillator model fits the behavior of molecular bonds at low energy levels. Let us apply these formulas to a practical example involving a cart on a horizontal air track. We are given a cart with a mass of 0.500 kilograms and a spring constant of 20.0 newtons per meter. The cart oscillates with an amplitude of 3.00 centimeters. To find the maximum speed, we use the formula square root of the spring constant divided by mass, then multiplied by the amplitude. Converting centimeters to meters, we calculate a maximum speed of 0.190 meters per second. If we want to find the velocity at a specific position, like 2.00 centimeters, we use our position-based formula to find that the velocity is plus or minus 0.141 meters per second. Continuing with our example, we can calculate the specific energy values when the cart is at the 2 centimeter mark. Using the velocity we just found, the kinetic energy is 1/2 times the mass times the square of 0.141, which equals 5.00 times 10 to the power of -3 joules. The potential energy at this position is 1/2 times the spring constant times the square of 0.0200 meters, giving us 4.00 times 10 to the power of -3 joules. Adding these together gives a total energy of 9.00 times 10 to the power of -3 joules. This matches the value we get from our general total energy formula, confirming our calculations are consistent. To summarize the key points of this lesson, we have learned that the total mechanical energy of a simple harmonic oscillator is a constant of motion. This total energy is calculated as 1/2 times the spring constant times the square of the amplitude. We have seen how energy continuously cycles between kinetic and potential forms throughout the oscillation. We also established that the velocity of the object can be determined at any position using the principle of conservation of energy. Finally, we discussed how simple harmonic motion serves as a robust model for many physical systems, ranging from mechanical springs to the vibrations of atoms in a solid. To conclude, consider these review questions to test your understanding. First, can you identify the specific positions in the oscillation cycle where the energy is split equally, meaning 50% is kinetic and 50% is potential? Second, think about the relationship between amplitude and energy. If we were to double the amplitude of the oscillator, by what factor would the total mechanical energy increase? Furthermore, how would that doubling of the amplitude affect the maximum speed of the object? Reflecting on these questions will help solidify the mathematical relationships we have discussed today.